Welcome to 5G in a nutshell, Part 5. If there were still some unanswered questions in Part 1 to 4, we can say that now, in mid-2021, we once again have a lot of new information and, above all, solutions. That's why we'd like to bring you up to date with the latest situation in code selective measurements for 5G mobile radio systems. Afterwards, we will answer various general questions on the subject of 5G measurements. But first of all, let's get to the point. How do I measure the exposure due to a 5G base station? The first important step in solving this measurement problem is to separate the two questions: how do I make a code selective measurement? And how do I correctly extrapolate to the maximum possible exposure, particularly when considering beamforming antennas? The code selective measurement is, of course, the basic for the extrapolation. It has become apparent that the best solution is to measure the secondary synchronization signal SSS. A new software option for the Narda SRM 3006 enables measurements of the SSS for frequency range 1, FR1, which goes up to 6 GHz. The second step, extrapolation to the maximum possible exposure, is not quite as easy as it was for 3G or 4G LTE. Whereas for these it was just one simple factor that was usually the same for all measurement situations with the same bandwidth, there can be three different factors for 5G new radio with beamforming and TDD. In particular, the beamforming is dependent on the measurement location. For this reason, extrapolation for 5G is not performed on the SRM but externally, such as on a PC. What steps must be considered when measuring the exposure? Now, the first step is to measure the SSS reference signal. The SRM 3006 can do that. Since the signaling block only occupies a fraction of the possible spectrum, the next step is the first extrapolation, which is to the full bandwidth occupied by the service. 5G often employs so-called TDD systems. If this is the case, the result must be corrected by the TDD factor. And finally, there is a beamforming factor. If beamforming is being used, the antenna gain for the signaling, including the SSS that we measure, is less than the antenna gain for the traffic beam. Naturally, the result must be corrected upwards by this factor, since we want to determine the maximum possible exposure. Once we have done this, we have the result of the maximum possible exposure. This is a value that many national bodies and authorities specify for the protection of the general public. Let's look again to the advantages of the code selective measurement. Code selective measurement with extrapolation makes the measurement result independent of the actual loading of the base station. The result is the same whether the measurement is made at 3 p.m. or 3 a.m. It also makes it possible to separately evaluate every single cell and every segment that it contains. And, especially important for TDD systems, radiation from cell phones in the vicinity does not affect the measurement result. Even though they transmit in the same frequency band as the base station, the code selective measurement suppresses their storm of interference. The extrapolation to the maximum exposure based on this ensures a watertight assessment of the location. Even with its entire output power focused on the point of measurement, the base station cannot exceed this value. If you take a frequency-selective look at the signal from a 5G system versus time, measured here using the Narda Signal Shark, the signaling stands out clearly when the load is low. If, however, the service is heavily used, the signaling can only be separated from the payload signal with difficulty. At this point, it becomes obvious that the code selective measurement has a clear advantage when the load is high. If you look at the SS PBCH block using the high-resolution IQ analyzer of the Narda IDA, you can directly compare the theory with practice. The SSS part can be recognized and measured, for example by using markers. But, as mentioned, that only works at a low load. and also requires the fine art of zero-span measurement on a spectrum analyzer together with an excellent knowledge of triggering. How good that SRM has the 5G option, which makes live and the measurement of the SSS much easier. Simply select the 5G new radio operating mode from the main menu. You still need to tell the SRM the signaling center frequency, the measurement range and the subcarrier spacing SCS. That's enough for most cases. The signaling center frequency for 5G isn't necessarily the same as the service center frequency like it is for 4G. The signaling frequency can be chosen freely in a wide framework within the assigned spectrum. For example, in this measurement screen, the signaling is at the lower end of the frequency band. In most cases, though, this frequency is relatively constant. So once it has been found for a particular operator or manufacturer, it can be saved in a setup or service table and recalled whenever needed. Selecting the measurement range is the same with this option as with all other operating modes. And if you are not sure, the SRM will help you out with the measurement range search function. The subcarrier spacing SCS is a defining parameter of 5G. The SCS for 4G was fixed at 15 kHz. In the 5G frequency range 1, however, the system can dynamically switch between 15 kHz, 30 kHz and 60 kHz depending on the required system performance. However, this applies only to the traffic. Once set, the signaling is fixed and remains constant at either 15 kHz or 30 kHz. 60 kHz is not used for signaling in frequency 1. If the SCS is not known, it can be easily found by trial and error. There will only be a measurement result when the value is set correctly. You can now optionally select the sensitivity for the calculation and the displayed measured value. Sensitivity can be set in 3 stages. In this case, though, it is not the physical measurement sensitivity of the instrument, such as the displayed intrinsic noise. This is the sensitivity of the evaluation or algorithm. By now, you should have some measurement results, and you can select which of the 8 possible secondary synchronization signals SSS that you want to display. Or maybe just the highest of the 8 SSS max. Or the sum of the square of all 8 SSS signals, SSS sum. This will depend on your particular national measurement regulation. Whatever the case, the SRM always measures them all at the same time. The results display in details. First, the index. This is assigned by the SRM. Second, the cell ID. This is transmitted by the base station and serves to identify the base station and the segment. The value is obtained by the SRM by decoding. Third, the number of SSS the SRM has found. If this stands at 1, then it is likely that there is no beamforming in operation. If the value shown is greater than 1, beamforming is definitely active. And finally, the results themselves. In this example, the first column shows the value of the highest SSS found at this moment. If you open this dataset by SRM TS, you can see all values at the same time. But let's just extrapolate on the basis of a measurement result table. For cell ID 8, the maximum field strength of the secondary synchronization signal is 2.091 mV per meter. And the SCS is 15 kHz. Otherwise, we would not have got any result. The SRM has done the bulk of its work here. What follows is more of an example. The precision of the extrapolation is in the hand of the respective national and international bodies. Switzerland has already published a pretty complete description, including accounting for beamforming antennas. You can find the description under this link. Narda will shortly make available further tools and articles concerning the subject of extrapolation and beamforming. We'll be happy to keep you updated. Step 2 is the extrapolation to the full bandwidth of the system. For example, if the spectrum analysis of the SRM indicates that, in this case, we are dealing with a 20 MHz system, then the following calculation is the result. With a subcarrier spacing of 15 kHz and a bandwidth of about 20 MHz, the approximate correction factor is 1333. The precise value, namely 1272, is provided by IEC. Step 3 describes the TDD correction factor. For example, if the downlink occupies 80% of the time, the correction factor will accordingly be 0.8. For the remaining time, the cell phone users have the right to transmit, or it is occupied by a guard interval, for example. If the system is an FDD system, that is, the base station can transmit in its assigned band for the entire time, then the TDD factor is 1. The definition of 3GPP allows 61 symbol variation. Whether they are all used is another story. Thus, for example, national operators have agreed among themselves to dispense with flexible adjustment and to synchronize the TDD signals with one another, even if they are operating at different frequencies. This ensures that one base station is not transmitting at the same time as a neighbor antenna is receiving. Priority here, then, for the quality of service across providers. The TDD factor can be checked and even determined using the scope option of the SRM. In this case, however, more traffic would be an advantage. Step 4 is a so-called beamforming factor. It would be beyond the scope of this video to determine this when beamforming is used. This is irrelevant to our example, since the SRM has only found one SSS, which means there is no beamforming active, so the factor is 1. The question of whether beamforming is actually likely can often be answered simply by looking. Beamforming antennas are much squarer than the non-beamforming predecessors. Step 5 is now evaluate the parameters obtained. Starting from the SRM result for cell ID 8 of 2.091 mV per meter, we multiply this measurement value by the square root of the product of the extrapolation factors. This results in a maximum possible exposure of 66.7 mV per meter at this measurement location. Assessment of cellular station is now quick and easy thanks to the new 5G new radio option. The extrapolation to the maximum traffic load gives you an always dependable result without any intervention in the system controls or direct participation of the operator in the actual measurement. There will be more information from Narda soon on the subject of determining the beamforming factor. Always get the latest information from our news ticker. We have answered some typical more in-depth questions on measuring 5G base stations in the video 5G in a nutshell FAQs. The Narda team wishes you every success in measuring 5G new radio stations. Bye bye.